So I'm going to talk about Gammapy, a Python package for Gammaray astronomy. And I'm going to present on behalf of the whole Gammapy team. Let me just adjust the microphone a little bit. Just a few words about myself. So I'm a postdoctoral researcher at the Center for Astrophysics in Cambridge. I'm a gamma-ray and X-ray astronomer, but I'm also an open source scientific software developer and like a self-taught statistician. I'm one of the lead developers of the Gammapy package. And this Gammapy package has been chosen as a science tools for the future Cherenkov telescope array. I'm going to talk about this a bit more. I'm also a member of the CHASC Astrostatistics collaboration, where I work on statistical methods for gamma-ray analysis of gamma-ray and X-ray data. Most of the work can be found on GitHub. I'm putting a link there. You can also find some more information about myself on my webpage. A very short introduction to gamma-ray astronomy. I think many of you might not be familiar with this. So just a very quick reminder. So this is the electromagnetic spectrum. And what I'm going to talk about is the data really at the highest energies. So we are talking here about particle energies above GeV. And there's the high energy range starting roughly at 1 GeV here. Then there's the very high energy range starting above roughly 1 TeV. And then there's the ultra high energy range, which even goes to peta-electron volts. What's important to keep in mind is that gamma rays are non-thermal emission, so there's no object in the universe that would be so hot that it could produce gamma ray emission via thermal emission. So gamma ray emission always happens via particle acceleration processes. And these are the things that we're interested in. This is just a picture of the Milky Way in multi-wavelength. So we know by now that the Milky Way is emitting like in all wavelength ranges, from radio to infrared to optical to X-rays and even gamma rays. So here at the lower part, and this is really the era of multi-wavelength astronomy. So we are able now to understand astrophysical processes across the whole spectrum. This is the GeV and TeV gamma ray sky as seen by recent instruments. So this is a map of or on the left side you can see an all-sky map of the Fermi-Lat. So this is in GeV range, and there are like all kinds of things going on. For example, there are active galactic nuclei, so there's short time variability in gamma rays. There's galactic diffuse emission, which really extends across the whole Milky Way. There are these so-called Fermi bubbles, which are extended features above and below the galactic plane. Then the other map to the right here, the large one, this is a map as measured by the Hawk Observatory. This is above 1 TeV. Again, you can see that the galactic plane is really bright in TeV gamma rays. And again, there are active galactic nuclei. One last example is the scan of the galactic plane by the HESS telescopes. This is shown at the bottom. And you can see that there are all kinds of sources popping up in TeV gamma rays, for example, pulsar wind nebulae. The galactic center is a very interesting source. Supernova remnants, young star clusters, there are really like all kinds of interesting things going on. And there are some questions related to this for example, where are the acceleration sites for these cosmic rays and cosmic particles? Can particles reach peta-electron volt energies? This is sometimes called the search for pevatrons. And we can also look for signatures, for example, of dark matter. So there are many interesting science questions related to this. This is an overview of the current gamma ray instruments. There are multiple classes of those. So first, there are the ground-based imaging atmospheric Cherenkov telescopes, such as HESS, Veritas, MAGIC, FACT, or then CTA. Those are pointing instruments with good angular and energy resolution. They have a very short duty cycle, and they can only operate by night. Then there are so-called water Cherenkov observatories, such as HAWK, LASSO, and SWGO. They have an all-sky coverage and a long duty cycle, but they have poorer angular and energy resolution. But they also have a large collection area, so they can really measure up to very, very high energies. And then there are satellite-based instruments. This is typically just now the Fermi-Lat instrument. This has good angular resolution and energy resolution, but it has a very limited effective area and can only measure up to a few hundred GeV. What's important here is that all these observatories have really complementary properties. And up to now, one could not really make advantage of all the data that they take, because the data could not be combined. This is the future of the gamma ray telescopes. So there's going to be the so-called Cherenkov Telescope Area Observatory, which is going to have 2 sites. So this is, again, an imaging Cherenkov telescope, but this time a much, much larger array. There's going to be one observation site in the south and one in the north to cover the whole sky. And as you can see here, so this is the sensitivity curve, and the one shown in black and red, this is the one expected from the Cherenkov telescope, and this is going to improve the sensitivity that we can observe the gamma ray sky with by a factor of 10. And also the angular resolution is going to be improved by a factor of 3. Also, for the first time, and this is important, this is going to be operated as an open observatory. So up to now, with the other instruments, the data was closed, and the same for the software. But the Cherenkov telescope array is going to be operated as an open observatory with open data and open software for everyone to analyze. Gammapy has been selected in 2021 as a library for the Cherenkov telescope science tools in an internal selection process. A very short introduction to gamma ray data analysis. So all these observatories are basically particle detectors. So they measure events, and then they're trying to reconstruct the initial properties of those events. So things like energy, position, arrival time, and then those are just put into a list of gamma-like events. There's some background involved, like hadronic particles, for example, that look like gamma ray events. But this is dealt with later. And then those events are binned into a counts map or image. Typically, this is hyperspectral imaging, so we have a list of images or a 3D cube of your data. And then in the analysis, one tries to model the emission using a model or using Poisson log likelihood fitting. I've shown the formula here, but the details doesn't matter, so one assumes Poisson statistics per bin, and then you can sum up over all bins to get the likelihood of your measurement here. In addition, there are templates then for the hadronic background. This is also what I'm showing here. Then in addition, there is a data model or a model of the instrument response. So each observatory or each telescope has a unique instrument response involving a limited point spread function, a limited energy resolution described typically by something called an energy dispersion matrix, and then there's something like an exposure, which involves the observation time and the effective area. And then one just assumes a certain parametric source model, something like a spectrum or a morphological model for the source. This is forward-folded through the instrument response to get an estimation or prediction for the counts that are to be expected when measuring or observing the sky. The interesting thing here is now that this multiple measurements of multiple instruments or multiple measurements even of the same observatory but of the same object can be combined into a joint likelihood. So one of these likelihood terms includes the instrument response, but this could even be, for example, for Fermi, CTA, or HESS telescopes. And then you can combine all these likelihoods to get something like a joint likelihood or total likelihood, and this is then just optimized by finding the maximum likelihood. In this way, you obtain best fit parameters, which you then report in your publication, including errors. This includes parameters like total flux of the source, spectra indices, or morphological parameters such as size, position of the object. So this is really the main idea of Gammapy. So we have these pointing gamma ray observatories, we have these all-sky gamma ray observatories. And up to now, they could not really collaborate because they all had their internal data formats. They had their data in very different formats. They had their own software. And the idea was now to introduce a common data format that all of these observatories can export the data to, and then use a single Python package, in this case for the analysis of the data, to obtain really sky maps, spectra, and light curves. So the quantities we are then interested in the end. So Gammapy has a few dependencies. So it's built on the scientific Python stack. So it uses AstroPy, SciPy, and NumPy as the main dependencies. So AstroPy to handle sky coordinates, SciPy for things like interpolation, minimization, FFT convolutions, NumPy for the ND data structures. Then we have a few additional dependencies, such as Pydantic, which we use for the configuration system. Then we have PyYAML for YAML IO, Matplotlib for visualization, and Click for our command line tools. Then we have a few optional dependencies, such as Sherpa and iMinui for the minimization processes. We have HealPy for handling Helpix maps. I'm going to talk about this a bit more later. And also Jupyter for tutorial notebooks for users. Just a quick note on the development and CI setup. I think this can be always interesting to share this kind of information. So we're hosted on GitHub. We're using GitHub Actions to run a CI system on each pull request and also a release pipeline. We use a service called Code Coverage to monitor our code coverage to see how well it is covered by tests. Our docs are built and deployed using a custom GitHub action that we implemented. For building the documentation, we use Sphinx, and for testing, we use PyTest. In addition, we have a few pre-commit hooks to ensure that the format of the code base is consistent. So we use black code formatting everywhere, and we use isort to automatically sort and format imports, and also check for the PEP 8 standard. Here's just some more code statistics. So in total, we have roughly like 50,000 lines of code. 1/3 is in the Python API, roughly 1/3 is in doc strings and documentation, and another 1/3 is in Python tests, and then there are a few smaller things. I think we've achieved roughly like a healthy distribution of these things, but we're still trying to improve on documentation and testing. There's a small amount of Python code involved, where we re-implemented certain masked NumPy expressions just to speed up very critical parts of the likelihood maximization, but this is really just like 100 lines of Python code with very specific functionality. This is the subpackage structure of Gammapy. So Gammapy is structured into multiple subpackages, which correspond to the different levels of data reduction that you have for Gammaray data analysis. So you start from these gamma-like events. For this, we have a package called Gammapy data, and to handle the instrument response, we have a package called gammapy.iif. Then the data is reduced, which means it is binned into these 3-dimensional data structure, or sometimes 2-dimensional or 1-dimensional. This is called Gammapy makers. And then we have the bin data, which is represented by Gammapy maps and a combination of multiple maps, which is called a data set. And then the final step is modeling and fitting. And for this, we have Gammapy modeling and Gammapy.estimators, which do very specific hypothesis testing scenarios. And in the end, then you end up with the science products, such as those catalogs, sky maps, spectra, and light curves. In addition, we have a high-level interface, which is called or stored in Gammapy.analysis, and this allows users to execute these analysis workflows based on a high-level configuration. Let me just show you some code examples. So this is a code example using Gammapy maps. This is the most important data structure in Gammapy, and we have spent a lot of effort to define a uniform API for multiple pixelization schemes. So as you've seen, Gammapy can deal with data from all sky instruments and pointing instruments. And for this, we need an all-sky data structure, which is represented by Helpix. Then for pointing instruments, typically WCS projections are used. And sometimes also one is not really interested in the spatial information, and one is just looking at spectra. And for this, we have a region-based API. And what we've achieved here is basically the same API. As you can see, when you create those objects, you can just choose which map type you have. So it's a WCS, Helpix, or region-based analysis. And this way, users can use the same tools just with these different data structures. We have support for multiple extra axes, so non-spatial axes, those things like an energy axis or a time axis or a label axis. There's some overlap in functionality, for example, with packages such as NDCube or AstroPy NDData. However, there are a few things which are very specific to Gammaray data, so mostly this common API. But also we're interested in keeping track, for example, of the bin edges and centers at the same time. But it would be nice, for example, to maybe collaborate more in future with these other packages. This is an example for Gammapy makers. So this is the data reduction chain that we use. This API was heavily inspired from scikit-learn. So the idea is that you have a maker which represents a step in the data reduction. And this step can be configured on init, and then you can build a data reduction pipeline by chaining multiple of those makers, and then execute it by passing in your data structure. This also allows users to define data reduction chains as a total, but also like custom data reduction steps via a registry system. And then this whole process can be configured and defined also from YAML-based configuration files. One last example, so these are Gammapy models. So typically, gamma ray data can be modeled up to in four dimensions. So one has a spectral part, a spatial part, and sometimes in addition a temporal part. And this is handled by multiple classes that then are combined into this sky model object here at the end. We have a complete gallery of all the built-in models in Gammapy for this, so the selection of built-in spectrum models, spatial models, and temporal models. But users can also implement their custom models to achieve very specific analysis goals, such as measuring an energy-dependent morphology of a source or something like this. And then those custom models can be, again, registered via a registry system. All the models can be serialized also into YAML and then be read back for analysis. Let me just show you a few quick analysis examples. So this is one just visualizing the instrument response of multiple observatories. This seems trivial, but just to highlight this, so the fact that you can do this with a single software, this really represents a lot of work from the community to equivalent of maybe a few years of work. Here's another example. This is a spectra analysis of simulated Cherenkov telescope array data. This is a somewhat classical gamma ray analysis where one is trying to estimate the background from these ring-like features here. And then one measures the spectrum in given energy bands. What Gammapy here brings on top is that actually for each of these energy bins, the likelihood is exported and is made available to the user. And this is much more information than is typically provided, because typically you would only have something like an error, 1 sigma error, maybe an upper limit. Here's another example that shows how you can actually combine data with Gammapy. So this is SpectraFit combining data from Fermilab, MAGIC, and Hawk. The combination of the data really leads to much smaller errors. So this we've shown in one publication. And also via Python wrapper classes, you can actually interface to third-party packages that do then astrophysical modeling of the emission. So typically you have processes like inverse Compton and their astrophysical model of those, and you can directly fit those to gamma ray data then using Gammapy. We have a whole set of tutorials. Here's the quick gallery covering data exploration, package, and API. There's also an introduction. We have multiple data analysis examples and analysis threads. And we aim to provide users with a selection of the most important analysis scenarios, as well as like API-specific tutorials to learn, for example, about the Makers API, about the Maps API. In total, we have 37 tutorials, and those are supported via the Sphinx gallery. And this way, you can also directly execute those in Binder. There was some work related to science validation of Gammapy. So there were 2 papers reanalyzing published results from the Hawk Observatory and the HESS experiment using Gammapy for multiple sources and analysis scenarios. Thank you. Yeah, that's still working. And both found excellent agreement between the reanalysis and the previously published results. We found that this was very important work for the sub-communities to really convince them of the quality of the results of open source software, because there were really doubts and it took years to convince those communities. We really found that the acceptance of Gammapy increased noticeably within these communities after those papers have been published. So we hope that further work follows, for example, for Lasso or Veritas. We also ourselves, as a Gammapy community, wrote a paper on the 1.0 version. So in the past, basically 1.5 years. It was written collaboratively and openly on GitHub. I've put the link here so you can basically see the full history of the writing. It uses a tool called Show Your Work to make the paper reproducible and automate the build process. The paper has now just been accepted for publication by Astronomy and Astrophysics, and it's going to be in preparation and published very soon. It will serve as a main reference for the long-term support version, together then with the exact version used in publications via Zenodo. It provides academic credit to the contributors, which is really important for their career development. So I think this is not something that we should forget. Just a few words about the Gammapy project itself. So Gammapy is not only a software package, but a community of gamma ray astronomers interested in collaboration on methods and open and reproducible science. This is the project organization. So there are project managers, lead developers, and sub-package maintainers. And then, of course, like a large part of contributors. Those roles are not elected right now, but just like assigned on a voluntary basis, just because we do not have so many people that contributed so far. We have a system that is called Proposals for Improving Gammapy. This is basically exactly the same as a PAP or a NAP. And in addition, we have a coordination committee which tries to promote and coordinate and steer Gammapy developments. And this consists of representatives of contribution institutions. I think I'm running short on time. Sorry? Oh, it's negative time. Okay. Okay, I have to speed up in this case. So let me just say a few things. I'll just skip two slides. So we're also organizing coding sprints and dev meetings. This we found very useful to really maintain a healthy community, and I can really recommend doing this. We have user support and community support via Slack and GitHub. So in case also you want to reach out to me later after the conference, you can really use one of these channels here. So outlook and summary. We have some future developments to do. So the development of LTS versions are coordinated via roadmap documents, which are again PICs. Now we are planning for working on the roadmap for version 2.0. Some topics that we have to address are a fully configurable API. We plan to do this via Pydantic, and improve metadata handling. Also, again, we plan to do this via Pydantic, and then support for a hierarchical model and parameter priors, and also finding a solution to support distributed computing and GPU support. So currently, Gammaray data analysis are very small, but they are going to grow. So if you have some experience with this, please talk to me. So Gammapy is an openly developed Python package for Gammaray astronomy in a major state, marked by the 1.0 release. It's ready to be used for Gammaray data analysis of all kind. It has currently an estimated user base of 200 to 300 users, but it is expected to grow even further. In general, there's some exciting science expected with the Cherenkov telescope array in Gammapy in future. However, the scale of these analysis will really grow, so we have some work to do on really getting scalable analysis with Gammapy. So thanks a lot for your attention.
All right. Ooh, fresh batteries. Wow. Thank you, Axel. We have some time for questions. If you have a question. I also note that there are Gammapy stickers downstairs. I think.
There are?
On the NumFOCUS, isn't it? No? No? Okay. Then you have a similar logo to someone else.
But I think I actually have some in my backpack, so if you're interested, you can talk to me.
Hi, great talk. Can you say a little bit more about the fact that you have the imaging detectors and then you have the water-based detectors, and like, were the challenges with supporting both those communities, or like from the ground up, was that intended to be one package for?
That's a very good question. So from the ground up, it was not intended. So Gammapy was initially developed only for the imaging Cherenkov telescope community. But then with a bit more digging into the data structures, we found that at a certain data level, you can represent the data in the same way. And this means you have a list of gamma-like events, and you have some representation of the instrument response. And the main way those instruments differ are in the instrument, or in the way the instrument response is described. For example, for these water Cherenkov observatories, they typically differ or just vary with the declination, while, for example, for the imaging Cherenkov telescopes, they differ with atmospheric conditions and all these things. But there are ways to handle this by keeping the initial data format rather flexible, and we found this to mostly work. We might encounter some limitations in the end in the amount of data, because the water Cherenkov observatories, they have a much higher background rate, so they have much larger event lists, typically of like gigabyte up to terabyte size, and this is just currently not possible to handle with these with the current state of the software.
Thank you.
I think we can do one more.
Okay, if no one else has one, I'll abuse chair privilege. So excellent talk. So I noticed in one of your slides you mentioned that you can export your models to YAML. So currently in the high energy physics world, we're trying to work on a serialization standard so that we can build models and then execute them across different tools. So is the model, like I guess schema that you have with Gammapy, is this something that is adopted across other tools in the astrophysics community, so that if if you want to build a model with Gammapy, you could then share it with someone else who doesn't necessarily use Gammapy for their analysis, or is it much more kind of baked into the pedantic model that you have right now?
The answer there is, unfortunately, there is no standard. So there are other tools that allow you to do model fitting in various kinds. Also for Gammaray astronomy, there's a tool called 3ML, for example. Also AstroPy has some functionality related to this, but AstroPy has chosen the ASDF format because the model definitions are much more complex. So there is currently no standard. I think the only benefit that you can say is that YAML is simple enough that it's not too much work to convert. But it would be nice to have a bit more standards related to this. But I guess that's usually how it is. If someone comes up with a new standard, then you just have one standard more.
Yeah, very much. Thanks so much. Okay, I think with that, we're also kind of at time. So we want to make sure that everyone has enough time to get to the next talk or hang out here for our next talk as well on LibYT. So let's once again thank our speaker,